In this section, we're going to discuss line integrals. And the phrase line integrals can be a little bit misleading. When you think line integrals, you might think the length of a line, but it's actually not. When we talk about line integrals, one way to think about it is looking at an area, and I have that in quotations because in this case, the area could actually be negative or zero. It doesn't have to be positive, of a curtain formed between the curve and the Z surface. So if you look at this first diagram and you look at some curve in the XY plane, it'll correspond to some curve on our surface. So when we think about a line integral, we can think about finding the area of this curtain. Now remember I said that it can be zero, it can also be negative. Think about having our z function below the xy plane. And in that case, when we compute our line integral, it'll turn out to be negative. One way to think about this is to think about a net area. So if you have part of our z surface above the xy plane, maybe part below, and you compute the line integral, it could also happen that it turns out to be zero. The formula for a line integral, if you notice this integral has c for curve, so we're integrating over a curve, some function z, and notice that this is a ds. This ds is integrating with respect to what we call arc length. Typically, when we define our curves, we do not define them in terms of arc length. We just use some random parameter t, or we just use some function xy or xyz. So if we look at this second diagram, this is what we mean by arc length. When we talk about arc length, we're talking about the length of the curve or its arc between points. For example, if we look at the starting point, s sub 0 is the arc length at the starting point, which is 0. The next point we get to corresponds to an arc length s sub 1. So that arc length s sub 1 is simply the length of our curve from s sub 0 to s sub 1. What corresponds to that arc length is this point xy with respect to arc length. And then that again will correspond to some arc length on our surface z. So again, it's an integral. If we look at this delta s being the arc length distance, and we look at that limit as that goes to 0, then we get our integral. This is what we have in the box below when we talk about the definition of a scalar line integral in the plane where we have arc length as a parameter. So let's look at the scalar line integral. That just means the integral or the integrand is a scalar function. It's not a vector function. However, the curve that we're integrating on, and here in our integral, we'll use C for curve. So we have this nice smooth curve that we'll call R of S because it's being written in terms of arc length. That can be a vector function. So the curve can be written as a vector function, but the integrand is a scalar function. Okay. Again, the difficulty is this integral is written in terms of arc length, which is typically not how we define our functions. And then if you look at the right-hand side and you take the limit as our delta s goes to 0, that's just the Riemann sum definition for this integral. Okay? And the reason why we want the curves to be smooth is we don't want sharp corners or cusps, because remember that it's not differentiable at a corner or a cusp. So if the curve does change direction and there's a corner or a cusp, you have to define the integral in pieces. So you have to separate it into pieces. Okay, there is some alternate notation that we use. And we can look at it as the function defined on the curve, which is written in terms of a vector r. Notice again, the ds has to be there because that tells us what we're integrating with respect to. So shorthand, we can just write the function xy, ds has to be there, or we could simply put in the function f. But again, the ds has to be there because it's indicating to us that this integral only works if we're integrating with respect to arc length. In example 1, we want to evaluate this line integral. So we're given this integral over some curve. The integrand is xy. Notice that's not a vector function. That's a real scalar function. We're integrating with respect to arc length. So I need to know what my curve is. I need to define it. So my curve is the unit circle. And it's given to me as r of s. So r with respect to arc length is cosine of s sine s. And here arc length s goes between 0 and 2 pi. So since I have my curve defined in terms of arc length, all I have to do is just plug all this into my integral. My curve c is going from 0 to 2 pi. So it's just the integral 0 to 2 pi. X, well, what is x? Remember, r is written in terms of x, y. So my x is cosine of s. And there's too many s's, so I'm going to put parentheses around the argument s. And my y is sine of s. And that's just ds. I think I'm going to do a substitution. I'm going to let u equal sine of s because I know that du will be equal to cosine of s ds. Now typically I change my limits of integration as well, but I'm not going to this time. I'm just going to leave them off and write this as u du, and my derivative is u squared over 2, and then plugging back sine squared in terms of arc length over 2, I'm now evaluating this from 0 to 2 pi. And I could have changed my limits of integration, but I don't want to. And I'll show you why in just a second. You can though. So notice that sine squared of 2 pi is 0. Sine squared of 0 is 0. So this is simply 0 minus 0 or 0. So remember, I said that this line integral can be equal to 0. Now also notice that if I did decide to change my limits of integration as well, I would have that my u value, which would be sine of 2 pi for upper, that would give me a u value of 0. The lower limit would be sine of 0, which would be a u value of 0. So I would be simply looking at the integral from 0 to 0 of u du. And whenever you're integrating and your upper and lower limits are the same, that's simply 0. So yes, you can change your limits of integration, or you could leave them off, substitute back, and use your original limits of integration. In both cases, we get 0. So let's say that we are going to use another parameter besides arc length. Well, in theorem 16.1, it's going to give you the transformation from arc length as a parameter to any parameter t. And when we do that, we have this Jacobian, which is the magnitude of the derivative of r. And then now we can integrate with respect to t instead of arc length s. So again, this is just a simple transformation. So what happens is this magnitude of r prime dt, that is simply r ds. So remember, the magnitude is simply the square root of, and it's the magnitude of r prime, so that would be the square root of x prime squared plus y prime squared. So this is the way that we can go from arc length to any parameter t, which is going to be helpful for us because typically when we do define our functions, we don't do it by arc length. Below is the procedure for evaluating a line integral and going from arc length to any parameter t. So first of all, number one, we want to find a parametric description of c in the form of some parameter t. Compute the magnitude of r prime, or the Jacobian, right, because it's a transformation, which is simply the magnitude of a vector square root of, in this case, derivatives squared. Add them together. The integrand will be written in terms of some scalar function with x's and y's in it. So you're going to have to, given your curve, you're going to have to substitute the x and the y values of your curve into the integrand in your function. So again, this is all just words. Let's go ahead and compute some examples. Example 2, we want to evaluate this line integral. The integral is x squared plus y squared, so notice this is not a vector, this is a scalar function or a real function. However, it's written in terms of arc length, which we don't want, because my curve is this line segment from 0, 0 to 5, 5. I don't know how to define that curve in terms of arc length. However, I do know from parametric equations that I can write this parametrically as x equal to x sub 0 plus at, y equal to y sub 0 plus b times t, where the slope of this line segment is equal to b over a, right? Y's over x's, rise over run. So all I have to do is find this parametric representation of my x value and my y value. My starting point 0, 0, that would be my x sub 0, y sub 0. So x is going to be equal to 0 plus, well, what's the slope? I'm going from the point 0, 0 to 5, 5. When I figure out my slope, it's simply going to be 5 over 5. I can reduce that if I choose. I'm not going to. I'm just going to let this be my b over a. X is going to be equal to 0 plus 5t, or just 5t. Y is going to be 0 plus 5t, or simply 5t. So what are my t values? This is really important because these are my limits of integration. Well, when t is equal to 0, I'm at the point 0, 0. When t is equal to 1, I'm at the point 5, 5. Now remember, this parametric representation is not unique. There's infinitely many ways to describe this line segment. So for example, if I took my slope m and I reduced it to 1 over 1, b would be 1, a would be 1. So my x would be t and my y would be t. My t values would then range from 0 to 5. Okay. However, I'm going to keep this the way it is. What is r? Well, r is simply, first component is the x, which is 5t. Second component is the y, which in this case is 5t. And this is defined from 0 to 1. My integral is going to go from 0 to 1 of, what is x squared though? I'm now integrating with respect to t. So I have to replace the x squared and the y squared in my integrand with a function of t. And my x is 5t. So this is going to be 5t squared, or 25t squared, plus y squared is 25t squared. Now I want to multiply that by the magnitude of r prime. Okay, the magnitude of r prime of t is going to be the magnitude of the vector. We're just taking the derivative of each component. So the vector is the vector 5, 5. And that would simply be the square root of 25 plus 25, or 50. All right, so simplifying that, I could keep the square root of 50, but ugh, can't stand not simplifying. This is simply 5 square root of 2. So this would be 5 times the square root of 2 dt. And that's the integral that I want to compute. I could pull out the 5 square root of 2, since it's just some multiple of my integrand. And in fact, I can pull out the 25 as well, right? Because this is 25. Actually, 25t squared plus 25t squared is 50t squared. So this is 50t squared dt, and I can pull out the 50 to get 250 square root of 2 integral from 0 to 1 of t squared dt. Super easy. This is just, 250 square root of 2 times t to the third over 3 from 0 to 1, which is 1/3 times the 250 square root of 2. So we get 250 square root of 2 over 3. So that's it. If you're not given the curve in terms of arc length, you're going to have to define your curve. So you have to go back to everything you learned about how to define these curves parametrically with some random variable t. So you're really not concerned with whether it's written in terms of arc length or not, because going back to our integral, remember that the Jacobian is that magnitude of r prime. If it turns out that you did define your curve in terms of arc length and you just didn't know it, that Jacobian, or that magnitude of r prime, will just turn out to be 1. Okay? So it's okay if it's arc length. It's okay if it's not. You can always still use that same line integral and change everything to just some random t value. If we're in three-dimensional space, it's going to be exactly the same. You're going to have your smooth curve because it has to be differentiable at every point. In vector form, it would be some x, y, and z vector with respect to a variable t. Exactly the same. You're going to have the magnitude of r prime, that's your Jacobian, and your function written in terms of your variable t. So the magnitude is still exactly the same, square root of all the components squared. Let's evaluate this line integral. Notice that my integrand is x, y plus z, this scalar function. It's in terms of arc length, but I'm not given my curve. I have to define my curve. It's a line segment from one point to another. So since I'm starting at the point 0, 0, 1, that would be my x sub 0, y sub 0, z sub 0. But now we're looking at a vector in three-dimensional space. So remember, we're going to have a starting vector, which would be the x sub 0, y sub 0, z sub 0, plus t times a direction vector. So the direction vector is going to be PQ, which is Q minus P. And our direction vector is going to be simply 1, 1, negative 1. Oops, helps if I put a comma in there. 1, 1, negative 1. My curve is then going to be my starting vector 0, 0, 1, plus t times the direction vector 1, 1, negative 1. Since this is a line segment, I have to know my starting and ending t values. So when t is equal to 0, I'm at my starting point. When t is equal to 1, I'm at my ending point 1, 1, 0. Now the magnitude of the derivative, I'll figure that out first. Oh, well this is weird because I have my line written in terms of two vectors. So it makes sense for me now to combine this to be the single vector t, t1 minus t. So that would be a better way for me to write my curve because it's easier for me to identify the x, the y, the z, and it's also easier for me to compute the derivative and find its magnitude. So this would be the magnitude of the vector derivative is going to be 1, 1, negative 1. And the magnitude would be the square root of 1 plus 1 plus 1, or the square root of 3. Now my integral is going to go from 0 to 1. X is the first component, t. So this is t times y is also t. So this would be t squared plus, and then z is 1 minus t times the square root of 3 dt. Again, I'm going to pull that square root of 3 out. And then look at t squared plus 1 minus t dt, square root of 3. This becomes t to the third over 3 plus t minus t squared over 2. And then this is 1/3 plus 1 minus 1/2. Let's see, that's 5 square root of 3 over 6, I believe. Again, double check me on that. All right, so I am done with that. Example 4, we want to evaluate another line integral. But notice in this particular case, our curve is actually in two pieces. The first part is the line segment from point P to point Q. And the second piece is the line segment from Q to R. So since this curve is made up of two different curves, I have to write two different line integrals. So I'm going to define two line integrals, r sub 1 and r sub 2. My r sub 1, I'm going to have go from P to Q. And then r sub 2 will go from Q to R. R sub 1 of t is going to be the starting point, which would be 0, 0, 0 as a vector, plus t times the direction vector. So the direction vector is going to be q minus p, which would be 1, 1, 0. And then I could write that compactly as t0. And in this case, my t values are going from 0 to 1. Now, if this were the path of an object and t was time, when I write my second curve, I have to start at t equal to 1. However, this is not. Since these are two separate line integrals for each curve, I can start my second curve at t equals to 0 as well. So I don't have to be careful with that. So r sub 2 of t is going to start at 1, 1, 0. The direction vector is going to be r minus q. So that's going to be 0, 0, 1. Or in other words, this would be 1, comma 1, comma t, where my t values are also going to go from 0 to 1. So again, if this were an application problem and this was a path of an object, I would have to define my second curve so that my t values started at 1. So that would change it a little bit. But in this case, I don't have to worry about it. Let's compute the magnitude of the derivative for each one. So for r sub 1, derivative is going to be 1, 1, 0. And that would be the square root of 2. So for r sub 2, derivative is going to be the vector 0, 0, 1. And then when I take its magnitude, that would be the square root of 1, which is simply 1. And now the first integral, I'm going to go ahead and pull out the square root of 2 because I know I can. It's going to be the integral from 0 to 1. Now going back to the integrand, it's x minus 3y squared plus z. So my x value is t, my y value is t, my z value is 0. So t minus 3t squared but my z value is 0, so that's dt. So that's my first line integral. I'm going to add it to my second line integral, which would be the integral from 0 to 1. In this line integral, x is 1, y is 1, z is t. So this is going to be 1 minus 3, or negative 2, plus z is t. And that's it. We just compute these separately. The first integral is going to be t squared over 2 minus 3t to the third over 3, or t to the third, evaluated from 0 to 1, plus this second integral is going to be negative 2t plus t squared over 2, 0 to 1. So it looks like it's going to be the square root of 2, 1/2 minus 1, plus negative 2 plus 1/2. Let's see, I get I get square root of 2 over 2 turns into a negative minus 3/2. I think I'm just going to stop there. I'm not going to put them together, even though they have the same denominator. I'll just leave it like that. So an application of our line integrals is finding the average value of a function. So we can use these line integrals to find the average value of a function over a certain interval, and it's simply the line integral divided by the length of the curve. In example 5, we want to find the average value, so just be careful about what you're asked to find. If you're asked to find the average value, you can use this formula. So we want to find the average value of the function on the curve. This is the integral over the curve of x e to the y ds. C is the circle of radius 4 centered at the origin. So again, I'm not given the definition of my curve. I have to define it myself. So I know it's a circle and it's centered at the origin. The radius is 4. First thing I want to do is, since I'm finding the average value, I'm going to compute the length of the curve. So the length of my curve C is just a circle of radius 4. Where it's centered doesn't really matter. Remember that is going to be 2 pi r. In our case, it's 2 pi times 4, or 8 pi. So I have the length of my curve. I need to define my curve. However, it's a circle. Center is at the origin. Radius is 4. So I could write that as 4 cosine of t, 4 sine of t, going back to how we define circles parametrically. And here my t values are going from 0 to 2 pi, since it's the whole circle. What if it said half a circle? Then maybe from 0 to pi. Let me compute the derivative of r and then find its magnitude. So the derivative of 4 cosine is negative 4 sine. No, this is going to be, I'll just put it in here. Negative 4 sine of t squared plus derivative of sine is cosine, so 4 cosine of t squared, which is simply 16 sine squared plus 16 cosine squared. And if I factor out the 16, it's sine squared t plus cosine squared t, which I didn't even have to write this because you could probably see that sine squared cosine squared, that's just 1. So this is the square root of 16, which is simply 4. And now the average value, since I'm going to divide by 8 pi, that's the same as multiplying by 1 over 8 pi, is going to be the integral from 0 to 2 pi. My x value is the 4 cosine of t. My y value is the 4 sine of t. So this becomes 4 cosine of t e to the 4 sine of t multiplied by my 4, my Jacobian, dt. Now I think I'm going to pull out a bunch of 4s, or maybe just the Jacobian 4. Yeah, I think I'll pull that out. So 4 over 8 pi, that's going to be 1 over 2 pi. I'm going to keep the other ones in. The reason why I don't pull out the 4 in front of the cosine is I need to do a substitution on the exponent for sine t. And I could see that if I let u equal 4 sine of t, then du is going to be 4 cosine of t dt. And this becomes 1 over 2 pi e to the u du, and I didn't change my limits of integration because that's just too easy. I'll get 0. And this would be 1 over 2 pi. E to the u becomes e to the 4 sine t, and then I'm evaluating this from 0 to 2 pi, which would be e to the 0 minus e to the 0. And since that's equal to 0, this whole thing is going to be equal to 0. Again, if I went ahead and changed my limits of integration, then I would have my u values would go from 0 to a u value of 0, and this is simply the integral from 0 to 0 of e to the u du, which is 0. So the 1 over 2 pi doesn't matter. It's still going to equal 0. Moving on, we're going to look at what happens if the integrand is not a scalar function, if it's a vector function. This brings us to the line integrals of vector fields. So when we are talking about a line integral of vector fields, how you want to think about that is, let's say that we have some curve, and notice that our curve here in this particular diagram is circular. So we have this curve, and it's oriented in a certain direction. In this case, our curve in the xy plane is oriented counterclockwise. So we have an oriented curve, and when we say oriented, we just mean that it has a direction, okay? And it's a parameterized curve. Going back to vectors, remember when we talk about positive orientation, that means the direction that the curve is generated in, and in our case, that's counterclockwise. At every point on our curve, we're going to have a tangent vector. Here we're concerned with our unit tangent vector, which would be the capital T. So notice that these red vectors, if you look at any point on the curve, we will have a unit tangent vector. It's a unit vector because it has length 1, and it's the tangent vector that goes in the direction the curve is generated in. So notice these tangent vectors are going in the same direction that the curve is generated in. Okay, so let's say that we have this curve and we're just plopping it down into some vector field. Any vector field, doesn't matter what this vector field is. Well, at each point on this curve, we can find what's called a tangential component of our vector field. And that would be a vector defined as the magnitude of the vector at that point times cosine of theta, where theta is the angle between the tangent vector to the curve and that vector from our vector field. If it turns out that the dot product is positive or greater than 0, because again, when we have two vectors, it makes sense to talk about things like their dot product or their cross product. If the dot product is positive, we'll say that there's a positive contribution to our line integrals. Remember, our line integrals can be negative, positive, 0. So if it turns out that this curve that's plopped down in some random vector field, if it happens at each point that the tangent vector to the curve with respect to the vector in the vector field, if that dot product is positive, then the line integral will be positive in that instance. If it turns out that the dot product is negative, then it's a negative contribution to the line integral. So at that point, the value of the line integral is going to be negative. So remember, we're integrating, we're adding up all these values. If the net value is positive, then the line integral is positive. Or you could have a negative line integral, or it could happen that it's 0. So that would be if the dot product is 0 between the vector in our vector field and our tangent vector to the curve. So here's some property down here. Because our vector t is a unit vector, then if we take the magnitude of f times the magnitude of t. So remember that would be our dot product, which is why we're looking at the dot product here. And you multiply that by cosine of theta. Since the magnitude of t is 1, all you have to do is look at the magnitude of f cosine of theta, which is why we were looking at that computation on our curve. Then that would just be the dot product between the two. The tangent vector and the vector from our vector field. So our definition again is with arc length. So if we have some vector field f, continuous on some smooth oriented curve C, and here it's parameterized by arc length, our usual definition. Capital T or uppercase T is going to be our unit tangent vector at each point of our curve C, which is why it has to be differentiable so this tangent vector exists. And this tangent vector is consistent with the orientation, so it goes with the way the curve is generated. Then we compute the line integral over the vector field as the dot product between the vector field and the unit tangent vector, but it's a ds. It's with respect to arc length. Okay, again, working with arc length can be tricky. So let's go back to ds. Remember in the beginning, this ds was the magnitude of r prime of t dt. Think about what this unit tangent vector is. So this unit tangent vector, going back to our vectors, that would be the derivative of our curve over its magnitude. So notice that the tangent vector and ds, the magnitude of the derivative of our curve cancels, and we just end up with the derivative dt, which is how we're going to go from arc length to any parameter t, and that's in the box below. If you look at the line integral of the dot product of the vector with the unit tangent vector with respect to arc length, then any parametric representation of our curve with respect to the parameter t. Now, this parameter t, remember, this can be arc length, but it doesn't have to be. It could be any parameter t. And we can write our vector field as FGH, can be written as f dotted with the derivative of r. And that's because we are replacing t ds with derivative of r dt, and that's where it comes from. So you could write this in a variety of ways. They all mean the exact same thing. If we did compute this dot product, remember the vector field f is the vector FGH, and we know r prime. That would be the derivative of x, derivative of y, derivative of t. If you did compute the dot product and expand out, you would get this following representation of f times x prime plus g times y prime, and so on. And you can always just shorthand replace the x prime of t with simply dx, y prime of t with dy, and z prime of t with dz to get this third form. Says the exact same thing. Now, if you look at that third form and you decompose it back into its dot products, because this would be, oops, don't want that thick line. This would be the vector FGH, that vector field, dotted with dx, dy, dz. So another way that you can write this integral is this last form, which is simply the vector field dotted with the derivative of r. Okay, and they all say the exact same thing. Now this is for three-dimensional space. However, if you're looking at just two-dimensional space, our vector field is just FG. We have R is just XY. Then we have this shorter formula that's down here. We'll do some examples. Example 6, we want to evaluate this line integral. So we have the vector field is XY. And it's going to be on this parabola. And we're given the parabola as R of t equal to t comma t squared, where our t values go from 0 to 2. Well, I don't know if this is a parametric or a arc length representation. I don't know if t is actually with respect to arc length. So instead, what I'm going to do is I'm going to go ahead and I'm going to just write it in the other form, which would be the vector field dotted with the derivative of r dt. That's the form I'm going to use. So t goes from 0 to 2. My vector field is xy. So remember, t in our definition r, t is x, t squared is y. So this is simply the vector t squared. And I'm going to dot that with the vector of the derivative of r. And I could just eyeball that. Derivative of t is 1, derivative of t squared is 2t. dt. Computing this dot product, I end up with t plus 2t to the third. Which is super easy to integrate as t squared over 2 plus 2t to the fourth over 4, which would be t to the fourth over 2. All right, so that would be 2 plus 8, I get 10. And we'll do another example. Example 7. We want to evaluate the line integral. We have our vector field, which is the vector xy over x squared plus y squared. And we have our curve r of t, which is t comma 2t. Our t values are going to go from 1 to 6. So my vector field, I think I'm going to go ahead, remember this is my x is t, my y is 2t. I think I'm going to go ahead and write out my vector field as t comma 2t and see if I can simplify that a little bit. X squared would be t squared plus y squared is 4t squared. So my denominator is 5t squared. And I can write this as 1 over 5t, 2 over 5t. I wanted to simplify that a little bit before I actually put it in my integral. My integral is going to go from 1 to 6. I have the vector 1 over 5t, comma 2 over 5t. I'm going to dot that with the derivative of r, which is simply 1 comma 2 dt. And that's it. We just have to figure this out. All right, so this is going to be 1 over 5t when I do the dot product, plus 4 over 5t dt. 5 over 5t is simply 1 over t. So the integral from 1 to 6 of 1 over t dt, super simple. That's going to be natural log absolute value of t evaluated from 1 to 6. So it's going to be natural log of 6 minus natural log of 1 is simply 0. This just becomes natural log of 6. All right, moving on. We're going to apply line integrals to work, which is a common application. And that's because now we're talking about vector fields and vectors. We can look at work. And when we look at work, we can talk about a constant force versus a variable force. In these first two examples, we're looking at something very simple. We're looking at work where we're actually taking some force. We're going to take an object and we're going to move it horizontally in a straight line. So here, d is going to be the distance that this object has moved. It's a horizontal distance. And with respect to this vector f, we can look at this corresponding f sub x, which is simply the force along the x-axis. Or this horizontal force. Theta is going to be the angle between the force along the x-axis as opposed to the force itself that's coming at an angle. And then we can go ahead and compute this constant force by simply looking at the work done equal to the magnitude of the force cosine of theta times the distance that the object has been moved. So that is a work formula for constant force with horizontal straight line movement. Now let's say that the force that's acting upon this object is not constant, meaning it just changes. Okay? Since the force is variable, we have to add up the pieces as the force changes. And whenever we do that, it turns into an integral. So variable force involves an integral, where you're integrating with respect to the force as it changes. Okay, so look at this integral for work. Now let's say that we're looking at moving an object along any path. Well, it turns out that that is simply a line integral. When we look at the work done in a force field, which would be this variable force acting upon an object on some curve or some path, we would have our curve or the path here as our R. It still has to be smooth or else we have to break up our work into different integrals. And let's say that we have our unit tangent vector t consistent with the orientation of this curve. Then the work done in moving this object along our curve, it doesn't necessarily have to be this horizontal straight line, can be just this general work formula, which is simply our line integral. Or written in terms of any parameter t, it would be the force vector dotted with the derivative of our curve. In example 8, we have this force field, which is 2x comma y. We want to find the work required to move an object on the path consisting of the line segment from 1, 3 to 0, 0, followed by the line segment from 0, 0 to 0, 6. Again, this is an example where since I have two different paths, I have to define two different curves. So I'm going to do an R sub 1. R sub 1 says I'm going to start from the 1, 3, so that's going to be 1 comma 3. And I'm going to add the direction vector, which would be -1, -3. This becomes 1 minus t comma 3 minus 3t. So we can view that as the x and the y. My t values are going to go from 0 to 1. And then I'll define my second curve. Again, since the work is going to be broken up into two separate integrals, I'm not concerned with consecutive t values. I can start from the beginning, and the line segment from 0, 0 to 0, 6 has nothing to do with the other one. So that would be starting at 0, 0 and going to the direction of 0, 6. And that would be 0, comma 6t for my second curve. T values are still going to go from 0 to 1. Okay, so my first integral from 0 to 1 is going to be 2 minus 2t. Because remember f is 2x comma y, and x is 1 minus t, so 2 times 1 minus t is 2 minus 2t. Y is 3 minus 3t. And I'm going to dot that with the derivative. In this particular case, it's negative 1, negative 3 dt. I'm going to do these separately. So I'll figure out the work done on this first path. It looks like it's going to be the integral from 0 to 1 of negative 2 plus 2t minus 9 plus 9t dt, which is equal to negative 11 plus 11t dt. I have negative 11t plus 11t squared over 2 from 0 to 1. And then that's going to be negative 11 over 2. Negative 11, yeah. So that would just be the integral with respect to the first curve. The second curve is going to be 0, comma 6t dotted with 0, comma 6 dt, integral from 0 to 1 of 36 t dt. And that would be simply 36t squared over 2, which would be 18t squared from 0 to 1, and I get 18. So putting these together, I have negative 11 over 2 plus 18, and that should be 25 over 2. Okay, so since the work could be split up in two separate integrals, I didn't have to worry about having those consecutive t values going from 0 to 1, 1 to whatever. So we can use line integrals to compute work. And a major concept that falls out of these line integrals, besides work, is what's called circulation. And in fact, we're going to look at the end of this section, look at two major concepts. One would be this circulation that we're going to talk about now, and the next one would be flux. Circulation and flux will be talked about pretty much every section until the end of this course. Circulation is pretty much, now remember, we have some curve and we're plopping it into some vector field. So when we talk about circulation, what we're doing is we're simply adding up all the vectors that are going in the same direction as our curve. So it's all the vectors in our vector field that are going in the same direction as our curve. So if circulation is positive, that means that the vectors are going in the same direction as the curve. If the circulation is negative, the vectors are in the vector field are going opposite of the curve. If the circulation is 0, we can look at that as being either there's just as many positive as negatives, so they cancel each other out, or another common application would be, what if the vectors in the vector field are all orthogonal to our curve? And in that case, circulation would be 0. Now, when we measure flux, which is the second concept we're going to talk about here, what it's measuring is vectors orthogonal to our curve. So circulation is what we're talking about right now. Circulation in a vector field. If you look at this first diagram, this is an example where you see the blue vectors that represents our vector field, and we have our curve. All of those vectors happen to be orthogonal to the curve. And in this case, this would be the vector field. This is a radial vector field, right? Where it goes outward. So this is xy in this particular case. So in this particular case, if I have this curve that's circular, it's oriented counterclockwise, and I plop this down into this vector field xy, what happens is that with respect to this vector field, the vectors that actually are touching the curve are all going to be orthogonal to the curve. So in this case, the circulation is going to be 0 because none of the vectors from my vector field are going with the curve. Okay? So here circulation is 0. Let's look at this next diagram. This is the example of the vector field negative y comma x. If you look at this second diagram, you could see that the vectors are all going with the curve. This is remember this is a rotational vector field, and my curve happens to be a circle. So in this particular case, since the vectors of my vector field are going with the curve, this is a positive circulation. All right, so I'm going to change this color. What if, and I'm looking at this second diagram, what if my vector field was y comma negative x? So that's actually taking my original vector field, negative yx, and taking the negative. Well, that means that all the vectors would be going in the opposite direction. So in this case, the circulation is going to be negative. Right, so we can use line integrals to measure circulation, where we could have a 0 circulation. We could have a positive circulation, which would mean that most of the vectors are going with the curve. Or we could have a negative circulation. Most of the vectors are going against the direction the curve is generated in. Looking at the definition of circulation in this box below, we have a vector field. It's continuous on some region. And C is going to be a closed, smooth, oriented curve. So let's just pause a little bit. When we talk about circulation, it only makes sense if the curve is closed, because we're talking about how things are moving around. So when we talk about a closed curve, it could be, oh, I don't want that thin. It could be any kind of curve that is nice and smooth and has some sort of orientation. So closed just means that we start at one point, we go around our curve, and we end at where we started from. It's possible with a closed, smooth curve to have it overlap on itself. And that's fine, as long as it has some sort of orientation. And your starting point is the same as, oops, I'm going in the wrong direction on this one. Sorry. And your starting point is the same as your ending point. So a closed smooth curve can overlap on itself, but where you start, you have to end. And it has to be smooth, meaning no sharp corners, no cusp, and so on. So we have this vector field that's continuous over this region, and we have this curve that's closed, smooth, and oriented. When we compute our circulation of the vector field on our curve, it's simply the line integral. In example 9, it says compute the circulation. So just be careful about what you're being asked to find. Compute the line integral, compute the average value, compute the work, compute the circulation, right? So circulation means line integral. And we have our vector field, it's already given to us, and we also have our curve. So in this case, r of t is 2 sine t, remember that would be your x, and cosine of t would be your y. And my t values are going from 0 to pi over 2. So computing the circulation is simply computing the line integral. In this case, we're going from 0 to pi over 2. F is x plus 1, and x is 2 sine of t. So it's going to be 2 sine t plus 1, comma, negative y, negative cosine. And I'm going to dot this with the derivative, right? Because we're also using the vector field dotted with the derivative of r dt. So you could use either one. And the derivative here is going to be 2 cosine negative sine. Dt. And that's it. Okay, so it's the same thing we've been doing all along. It's just different words. Our dot product is going to give us 5 sine cosine. Plus 2 cosine. All right, so this is another thing I'm going to do. I think I'm going to take 5 sine cosine. Instead of breaking this up into 2 integrals, I'm just going to use a trig identity. Remember, 2 sine cosine is sine of 2t, but this is a 5. So this becomes 5 over 2 sine of 2t plus 2 cosine of t. This is not the only way you could evaluate this. I just didn't feel like doing a substitution and breaking it up into 2 integrals. Okay, so this is going to be sine of 2t becomes negative cosine of 2t over 2. So this is going to be negative 5 over 4 cosine of 2t plus 2 cosine becomes 2 sine. And then I just have to evaluate it. This would be at pi over 2, pi over cosine of pi is negative 1, so this becomes a positive 5/4 plus 0 minus at 0, this becomes a negative 5 over 4 plus 0. It looks like I have 9 over 2, right? Because that's 10 over 8. Did I say 9 over 2? Oops, sorry, 5 over 2. 5 over 4 plus 5 over 4, 10 over 4 is 5 over 2. All right, so that's circulation. Again, all it is a line integral. And now we're going to talk about flux. So flux, remember that previous diagram with those blue vectors? Flux is just measuring the amount of vectors in a vector field that's normal to your curve. In this case, we not only need a closed, smooth curve, we also need a curve that does not intersect itself. So that's what we call a simple curve. So it's a little bit more than what we needed for circulation. So in this case, we can't have a curve that, oh, I keep doing that. We can't have a curve that intersects onto itself. So you can't have that. It has to be a simple curve, meaning it closed, smooth, has a direction, but doesn't intersect itself. So again, when we measure flux, we just measure all the outward normal vectors. So since we're talking about normal vectors, we need to review our unit normal vector. So at any point on a curve, there's going to be 2 unit normal vectors in 2-dimensional space. There's going to be an inward and an outward normal vector. So remember, that's normal is just orthogonal or perpendicular. So the uppercase N, remember that would be our principal unit normal vector. And that uppercase N, that normal vector, goes in the direction that the curve turns. We don't want that direction. When we measure flux, we're looking at outward. That's what we're measuring, the outward normal vectors. So we're going to use this lowercase n, which would be negative principal unit normal vector. So it's the normal vector in the opposite direction of the principal unit normal vector. So instead of going with the curve, it's going to go outward. And it's still a unit vector. So in 3-dimensional space, but the curve is still in the xy plane. If you wanted to compute this normal vector, it's going to be orthogonal to the unit k vector 0, 0, 1 and the tangent vector to the curve. So since it's orthogonal to both of those, to compute this outward unit normal vector, it's simply the cross product of the tangent vector cross with k. And order matters. If you change it and you do k cross t, you will get the principal unit normal vector, that uppercase N. That's not what we want. The definition for flux is then, given our vector field Fg and some region, we're going to have a curve, a vector function, xy, smooth, oriented, does not intersect itself. Then to compute flux, again, we're trying to find normal vectors. Circulation, we're looking at vectors that are tangent to the curve or that go with the curve. So we dotted the vector field with the tangent vector. This case, we're trying to find normal vectors, so it makes sense to dot the vector field with those outward facing normal vectors. Now that's with respect to arc length. So it's actually easier to use the formula that it's f y prime of t minus g x prime of t, which would be the dot product of the vector field with the outward normal vector with respect to the parameter t. Okay, again, this is where the n is equal to t cross k. So this measures outward normal vectors. In the case where this turns out to be 0, then flux is 0. That would be the case where the vectors are going with the curve. So if flux is 0, then circulation could be positive or negative. That means that the vectors are either going with or against the curve. If flux is positive, that means you've got a bunch of outward normal vectors. However, flux can also be negative. If flux is negative, then those vectors are actually going inward. Okay, so positive flux, normal vectors outward, negative flux, normal vectors inward. Let's look at these diagrams to get a better idea of what we're talking about. So we have some point on our curve, and our curve here is, keep doing this. Our curve is in the xy plane, and it's plopped down in some vector field. Well, at every point, you're going to have a tangent vector that is going in the direction the curve is generated in. You will have our k vector. It's an upward unit vector in the direction 0, 0, 1. If you cross those two, t cross k, you will get your outward normal vector. However, if you change the order, you get that inward principal unit normal vector, that uppercase N. Okay, because remember, at every point on the curve, there's going to be 2 unit normal vectors, one going out, one going in. We're measuring the normal vectors going out. So since this is a dot product, again, this is the same as when we did our circulation. Since this is a dot product, if you dot the normal vector with the vector field and it's positive, that gives you positive flux. If it's negative flux. But remember, it can also be equal to 0. In example 12, kind of skipped and took some examples away. Find the outward flux across the unit circle with counterclockwise orientation. And we're given that the vector field is negative x, negative y. So this is the unit circle. First thing I want to do is I want to define this. R of t. Unit circle means r is 1, so this is simply cosine, sine, and since it's the complete circle, I'm going from 0 to 2 pi. Okay, so the unit circle is a nice closed curve. It doesn't intersect on itself. I can use that flux integral. So the integral from 0 to 2 pi is going to be f is negative x, negative y. So since x is cosine and y is sine, negative x is going to be negative cosine. Negative y is going to be negative sine. And I'm going to take that vector and I'm going to dot it with the normal vector. But then I have a problem. I don't want to compute the normal vector. So I'm not going to use this form. Go back to the box and look at that other form. Okay? It's f y prime minus g x prime. So let's go back. This is f and g in my vector field. I'm going to do the integral from 0 to 2 pi. F is negative x, which is still negative cosine of t. Multiply this by y prime. Y is sine, going back to r. Y is sine, derivative is cosine. Minus G is negative y. So that would be a negative sign. So I'm going to write plus sign times the derivative of x is negative sign. Okay, so it just depends on what you have. If you have that outward normal vector, then you can simply do the dot product. But I didn't have it and I didn't want to compute it. So instead I used that second form of the integral because I had all of that information. That was easy for me to find. Notice that if you did define that normal vector and you did the dot product, you would get to the exact same place we are now. So we have 0 to 2 pi. This is going to be negative cosine squared t minus sine squared t dt. And in fact, if you factor out the negative, it's cosine plus sine squared, which is 1. So this is simply the integral of negative 1 dt. And that's negative t, 0 to 2 pi. This is negative 2 pi, which is fine. That means that the flux is not an outward flux. If you compute flux and the answer is positive, that means you have all these outward normal vectors. What that means is that our flux is inward, which means that we have this vector field. It's a radial vector field, but all the vectors are going inwards to the origin. So it's some vocabulary. If flux is inward, we call that a sink. Going back to this box, if flux is outward, we call that a source. So if it's positive, that means outward flux, that means a source. If it's negative, inward flux, it's a sink. And that's it for this section. Okay? And we're going to be exploring circulation and flux a little bit more in later sections. This is a really long section. Okay, so that's it.